Understanding the Special Relativity Theory Using Lorentz Transformation, điện tử 75, February 24th, 2021. Hi everyone. Here I want to share with you my understanding of the theory of special relativity. I stumbled on the Lorentz transformation. That helps explain that theory very well to me. Prior to this point, I've read, I've studied, but nothing became as clear as it is once I follow the math that the Lorentz transformation uses. I'm not going to read off the slides. I'll let you do that at your convenience. And I want to stress that the Lorentz is a transformation that applies to points of interest, and I would stress moving points, and it does it such a way that speeds are compressed, and that reflects the fact that the absolute speed as viewed by a stationary observer remains to be capped or bounded at the upper end to the speed of light. One of the disclaimers I want to bring up here is this share my understanding, but it may not be correct, but I'm happy with that. If you have comments or questions, please drop me a note. Now let's talk somewhat about the details within the Lorentz transformation. We talk about two coordinate system. One we call O, the unprime, which is where the stationary observer is. One called the prime or O prime, that is the reference coordinate that reside with a moving observer. Let's say if we're sitting on Earth as a stationary observer, the moving observer might be on a spacecraft that flies by us at a speed of v quickly. And then we also have interest in any motion like of a point P, which is launched or sent away by the platform, on the moving platform. The key thing here to note is we want to minimize the complexity, so we're going to keep the direction of travel to be parallel to the x and x prime axis. So y and z and y prime and z prime can be ignored. They stay the same throughout the whole system. The transformation applies to moving points. For anything that has to do with dimensions and so on, it would complicate the matter, and it serves no interest because we want to talk about the relative speed and the absolute speed. We don't want to talk about things like dimension, whether they are shrunk or not. I think we can explain that in a different conversation later. Note that to simplify matter, the points of interest such as P will also have to be at the origin of O and O prime when time start. That means T and T prime are both 0. The key thing to take away from this is the mapping of points from the ordinary space into the Lorentz space does it and provide it with a non-uniform time on the Lorentz side. And the reason why this is the case is it allows the modeling of the compression of the moving objects in the Lorentz space, so that the absolute speed as seen by the stationary observer is bounded to c. And here I give you some details as what changes you expect normally for time and distance when time in the primary space, and primary here mean unprimed space, changes per second, and also when you talk about a point moving from one to another one by 1 meter, what changes in time and in y in I mean gamma in the distance. I highlighted this one in red because this is very important to keep in mind. It means that anything that goes beyond in front of the moving coordinate, the farther you go on the right hand side, that means you actually goes farther in distance, but also it takes you less time. So therefore, the speed of such object is faster than the speed of your reference, and there's a compression factor which we will talk about later that basically will converge all those points into a maximum which be then seen by the stationary observer as traveling at a speed c and or less. Gamma. Gamma, the definition of gamma is given here. And v is speed of the moving observer with respect to the stationary observer. And c is the speed of light. And the value of gamma will be equal or greater than 1. And it can be significantly large if the speed of v approaches that of c. We'll talk about more these in details. I'm not going to be spending a lot of time here. This is a sort of like a animation of this with respect to time. It should be noted that the distance from the object P grows with time here. As you see, it's getting larger and even larger. So it just sort of like showing you what happens when time changes from 1, 2 to 3 seconds and so on. Now, the max, the absolute speed is calculated by taking the distance divided by the time and plugging all the formulas in. It will come out to be this. And if you try with some values of v prime very high or equal to c, the speed will come out to be c and minus c. So this seems to be agreeable. Now, this is somewhat important to study, but before we go and study this in details, I'm going to show you the next foil. This one is the case for a speed of v which is pretty high, closer to c. And in this case, this v speed here is only half of c. And I want to flip back and forth to show you that in the higher speeds of c, all these points are compressed even more. And keep in mind, the distance from all to this point here is always c. And that's the speed of light, because when we talk about elapsed time between the time where that point P goes at 0 to this time, it's only 1 second in this example. And in this example, as time goes on, you can scale this thing larger and larger, but relatively speaking, well, pun intended, everything here will scale accordingly. So you don't have to draw this thing for different time values because they all have a component of t here. And in this particular case, t, you can put a 1, value of 1 in here. So I give you the value of gamma for this case and for the other case. As I mentioned, as the transform enforces the fact that as you move from one point here to another point, your time in the Lorentz space goes down, and that's this negative value here. And it is done such that to show that even though that point is further from your stationary observer, the time to get there is actually shorter. So that means your speed actually goes up. And the more you go toward the right-hand side, the higher the speed is. Now, that is the absolute speed. The relative speed with respect to the O prime origin is defined by these lines. And I'm drawing them to show the scale here. You see, this one is speed of C, and half of that in this line here, half of that mapped to the point where C is that the speed of that point is now actually only half of C, and likewise a quarter of C for these points here. The bottom line is, as you see maximum speed, half speed, and quarter speed, they all get compressed and they all got bounded by an upper limit. And at the time of 1, the value from this point to this point is strictly equal to C, as we show here. And that's the beauty in using the Lorentz transformation to show that all objects with reference to the moving coordinate still moving at the speed that is observed by that moving observer, be that c or something less. However, their absolute distance from them back to the origin and so on, so with their speed is bounded by this transformation. And the whole thing key off the fact that as you go toward the right hand side, you travel farther in distance, but you get there sooner. That means you go a lot faster. And the compression in time and space, and also the speed compression converges this so that it does not go on forever. Let's see. We talk about this in here where at higher V speed, the compression even more aggressive. But otherwise, there's nothing new on this graph. Now, summary. The Lorentz transformation basically map moving points. And we don't talk about dimension. And it goes, it makes such that to enable compression of speed, right? And the result in the Lorentz time and space is a non-time invariant, meaning time will vary with different location in the Lorentz space. The next 3 points basically talk about what we just described, which is to that mobile observer, the relative speed remains the same. The absolute speed as observed by a stationary observer, however, is limited because of the way the transformation works. The scaling factor and speed compression factors are determined by the speed of the mobile observer. The faster that mobile observer is with respect to the stationary observer, the compression is more aggressive. And then the faster the mobile observer is, the more compression happens. All right, so I give you some more links to my YouTube channel and my Facebook page here. The Facebook page is for the youth of Vietnam. Materials are mostly in Vietnamese. You have comments, questions, drop me a note or write me an email. Thank you for listening.